Okay, it's been a while since I've done one of these. What's the time? 9:56 p.m. All right, so let's try to get back into the saddle a little bit because I got a bit distracted, I guess. Stopped doing these and haven't really moved on from chapter 16. But recently I read chapter 17 of Operating Systems 3 Easy Pieces, and now I want to try and build a simulator based around that chapter. So chapter 17 was on free memory management, free space management. Yeah, that's not right. Hang on. Chapter 17 is on free space management. That makes more sense. Um, and basically, it looks at, I guess, the easy, like the more common context to think about is like the malloc API, or like in the standard library in C, how you have malloc and free, and it's like how does uh, that library keep track of the heap memory, we know what's been allocated and what's still free. How does it keep track of all that? So that's kind of probably the most obvious context in which free space management is important, but then also operating systems, because they are responsible for giving out memory to the different processes, right? Giving out memory for their address spaces. They also have to be aware of what memory is currently available and what's currently in use. So free space management, you also see that there as well. So that's kind of what this is about. This is like the two major contexts that the book talks about. And this gets annoying to do because of the idea that processes can request variable sized chunks. You think about using malloc, like you're allowed to ask for whatever number bytes you want. You can ask for 10 bytes, you can ask for 100 bytes, 1,000 bytes, whatever. So in that way, it's not so predictable what a memory region is going to look like, what an allocated memory region is going to look like, because you don't know how big it's going to be until runtime, until the user makes the call. So, if it was fixed size, this would be pretty easy because you just have a bunch of fixed size slots. Whenever someone asks for some region, you give one slot away, and then whenever someone frees it, you put that slot back. Like, it'd be very simple. But with variable sized chunks or slots, it gets tricky. The idea of external fragmentation is basically this idea of when users, do a bunch of allocations and frees, eventually you can get a bit of memory that looks a bit like this, where you have these free regions that are maybe quite small, and then when a request comes through for, in this case, 15 bytes, because the individual regions, the free regions, don't offer 15 bytes independently, this kind of request might fail, when that's really not fair because there are actually 20 bytes that are free in total. So you wouldn't expect a 15 byte request to fail, but because of this external fragmentation idea where the free regions are fragmented by the allocated regions, I guess, you might have issues like that. So, the free space management and the way free space management works and what its goals are is keeping track of where the free space is, right? Which memory addresses aren't in use yet, but also trying to minimize external fragmentation because it is a legitimate annoying thing. Okay, so there are some assumptions we can get through that as we code, but the basic idea of free space management is, I'll probably be using a linked list because it's simple, even if it's not necessarily the most efficient way of doing things. You can imagine, a linked list that where each node describes the regions of space that are free. So at the very start, the linked list might only have one node in it describing the entire heap because that entire heap is free essentially. And then if a user requests like 100 bytes, that node would be split. So one of the major operations we'll talk about is the splitting operation, where basically, is this working? Okay. The free list might look something like this, where the node, this is the head, and the node has like a size value, which tells you how big the free region is, like, 16 kibibytes. And then when a user requests like 200 bytes or whatever, what would happen is that node would be sort of edited to say the size, instead of being 16 kibibytes, would be 16 kibibytes minus the 200 bytes that were just allocated. So now the free space is telling us, okay, we had the entire 16 kibibytes, but now because the user requested 200, we'll give that 200 bytes, and then the remaining, the node will now reflect the change in size, the reduction in size. And then you can imagine if you free those 200 bytes, rather than having two separate nodes like this, like, size equals 200 and then size equals 16 kibibytes minus 200, rather than having two separate nodes, because these two guys represent two contiguous regions in space, regions in the memory, you might as well sort of merge them together and basically reform the original node, which is this guy. Like, you might as well remake the original thing. So this idea of splitting, like conceptually reducing the size of the nodes by changing the size field, so splitting, and then also coalescing or merging nodes is like the two major operations we see. So that's basically what this is saying. The operations that are applied on the free list, you've got splitting, and then you've got coalescing, basically merging. So that's kind of the two major operations we'll have to code up, and we'll talk about that a bit more. What is this? This is what I said. Okay, so this is the bit where it gets weird, because I guess if you think about the malloc idea again, the malloc function takes in a size, like a number of bytes, basically, an integer, right? Basically saying, this is how many bytes I want to allocate. I want allocated so that I can use it for my own usage. The free function, which frees the allocated memory, only takes in some kind of pointer, right? So this is integer, number of bytes, this is some pointer. And you might not have thought about this much, but the job of free is to free all of the bytes associated with this resource, right? So if I say int star array equals malloc, I don't know, 100 times size of int, this is probably meant to be some kind of array which has enough space for 100 integers, right? So it's 400 bytes for 32-bit integers. When you pass in this pointer into free is meant to know to free the entire 400 bytes. But we aren't telling free that the thing is 400 bytes. So the question becomes, how does free know to free exactly 400 bytes and not, only 4 bytes or 8,000 bytes or whatever, right? So this is part of the structure of the free list. Well, not exactly, I guess not exactly the free list, but whenever you do an allocation, like this 400 byte allocation, whenever you do that, you actually also allocate a little bit of memory for what we call the header. So basically, whenever you do a 400 byte allocation, you'll also allocate, I guess in this example, it was 8 bytes, a struct which contains the size of the allocation. So in memory, what you'll see, like if this is your heap, and you've got like addresses 0 and 1, byte 2, byte 3, etc. Wherever you allocated your 100 bytes, 400 bytes was 400 bytes. 400 bytes, right? Let's say this is address 100 to 500, right? So 100 to 499. No, wait, is this good math? Yeah. 100 to 499 is the 400 bytes allocated. Why is that? Anyway, and then 500 is like just off it at the next part, the next region. Right before that, 8 bytes before, at byte 92, you will have what we call the header, and the header will have the field for size and also this magic field. It's kind of like, it seems like a kind of identifier field, just to double check that this is a valid header and not some like random garbage memory. But the header is supposed to be paired with the allocated memory, right? This allocated memory here, it's paired with it to tell us how big the allocated region is. So whenever free gets called, and the pointer given will be that 100 byte spot will be the pointer given by the user will be here. What free will do is it will look 8 bytes back, look back to here, right? Accessing this header, see the size field and be like, okay, the size field says 400 bytes, which means from the original pointer given, if I take a 400 byte region, this is how much I have to free. This is the resource I have to get rid of. Okay. And then, yeah. Do I want to keep talking or is there anything else? Yeah, so it looks back a little bit and then it figures out the size value. So yeah, so an allocation for X bytes, like 400 bytes, actually uses 400 plus the additional 8 bytes to make the header. So that's what this is. So X plus the size of the header struct. Okay, embedding the free list. This was the part that I kind of got most wigged out by, so I think this is good to talk about. The free list, normally, the free list is a data structure, right? Well, I've been saying it's like a linked list. It might not necessarily be. You can use other data structures, like I think binary trees and stuff get used as well. But generally, data structures you'd expect to use, like if you're doing them in C, you might expect to use something like malloc or free in order to build up those data structures, right? Like if I was to write, when I wrote that, was it B-tree? I think it was B-tree, right? B-tree library thing that I wrote. I used malloc a lot, right? And I used free a lot. The reason why that's not really valid in this exercise is because malloc and free naturally use their own free list, right? So using malloc and free to then write my own free list feels like a bit of a cycle, bit of a weird dependency cycle that, the question is kind of, how did the original malloc and free do this if they didn't have a malloc and free to work with, right? So that's kind of the position I'm putting myself in. So, we'll talk about this function or system call, mmap. I forget what this stands for, memory mapping or something. And we'll be using this, I think, today. But basically, one of the major things we're going to be doing is in the heap, in the memory region that this free list is meant to be managing, we will actually be storing the free list, the structure that the manager is going to be using. So in the same memory that we're managing, we're also going to be doing all our bookkeeping, all of our storing. So that's why we call it I think that's why it's called like embedding the free list. Like it's embedded in the same region that all the other, memory allocations and stuff is happening. The free list itself, the bookkeeper, is also being put in the same memory region. So the way that it seems to be done in the book, at least, I'm not sure if this is necessarily like the only way to do this. I'm sure it's not, but just based on the diagrams in the book, how it seems to go is, the same way you have a header struct for the allocated regions, right? There's also a node struct, right, for the free list. So like type def struct, and then you should have a size similar to before, and you should have a next, right? So very much like a linked list, right? Next field and some kind of key or value field. And then this could be called like node T or whatever. Maybe I'll name it better on the actual code, but we like free list node T or whatever, right? The nodes. So at the very start, assuming there's not much else going on, in this heap, remember this is a heap region. This block here is a heap region. We will start with a singular node. And assuming the heap in the book is, the entire size of this heap is 16 kibibytes, which is the same thing as 16384 bytes. That's how you convert, by the way. You multiply by 1024. So this whole thing is 16384 bytes. Of those bytes, if this is the struct, right? If this is the struct for a node, in which case the size of this struct is 8 bytes. Therefore, 8 of those bytes, 8 of these 16384, will be used for this node T. And the size of it will be the size value will be 16. Will be this one minus 8, 16376. So the size value will be 16376, and next will be null. Maybe I'll just write null just so that save space. So these are the field values. So what is this saying? This is saying I am a node. I am a free list node. My size value tells you how much unallocated memory I am associated with. All this stuff down here. Not myself, I'm always 8 bytes, but everything beneath me that is free. And next basically is like, okay, it's a linked list, so it will point to the next node if one exists, or null if not. So that's what that is. When you do, I think I have a diagram for this. It's not very good though. So this is kind of the same diagram. I just didn't I didn't do the multiplication here. But 16 kilobytes minus the 8 is how much is free at the moment. When you do a malloc like this, what happens is, instead of having the node, right, the free list node, it gets replaced by the header. This green is a header struct, is the header struct. We've replaced, the first 8 bytes was originally a linked list node. It's been replaced by the header, the other struct. And then, in this case, the malloc was 150. So from byte 0 to byte 7, technically, inclusive, that's the header. And then from byte 8 to byte 157, that's the 150 bytes that gets used by the user. From there, our node, we have to actually create a node down here at the 158th byte for using 8 bytes. And we say the size of the free memory beneath me is 16218, apparently. Just trust the math, I guess. And next again is null, because again, it's a singular node at the moment. So hopefully we're getting this idea of like the nodes of the free list exist in the memory and are positioned in such a way that they kind of don't clash with the used memory, and also describe the memory just beneath it. Like, the node struct in red is just above the free memory that it's talking about. In the same way that the header struct over here, the 8 bytes over here, is just above or just before the used memory, that region down here. So this memory is like memory being used by the user. This memory is the memory that is like we're willing to give to the user. This is a header describing the size of this used memory, and this is a node describing the size of the free memory region. So if we do look at the next couple sort of things, malloc 500 is very similar. Knowing that this is kind of the start of our free memory, we sort of take 500 bytes from here. We replace this with a header, and so this was originally a node, right? It's become a header. We take 500 bytes, and the head pointer moves down to sort of down here. Like if this is my 500 bytes, and this is my 8 bytes for the header, then the head, this is getting confusing. The start of the free list gets moved down to here, and that's what happens here. So like I said, originally the start of the free list was up here. It got replaced by a header, right? The green, the information telling us how big a used memory region is. Then the actual memory is there. Then the start of our free list starts down here. This is a node, and the remaining free memory is down here. And then the last thing I'll say is when you free stuff, in this case, if the user gave a pointer to free this region over here, the top region, then what ends up happening is, instead of having a header which describes the used memory, this turns back into a regular node which describes the free memory, and this stuff, instead of being 150 bytes used, becomes 150 bytes free, because we know that right before it we have a node and not a header. And this next value, all these next were pointing to null before, this next will now point to that node we had before. So this is now starting to look a bit more like a linked list. We have our head node, up here, points down to the next free node down here, describing the free region over here. So blah, 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 that's fine. And then if we free again, same kind of idea. If we free the second guy over here, we'll know to turn this back into a node and not a header. This will become 500 free instead of 500 used. And that's kind of what happens here. But the extra step is we have to coalesce. Remember this idea of like, if we've got free regions that are kind of contiguous, like, this guy over here and this guy over here are basically contiguous. The only thing separating them is the node, right? But that doesn't really count. This node is associated with this free, so they're basically one big block. So this guy is next to this guy, so we might as well merge the free stuff here and the free stuff here. And by the same logic, this stuff can also be merged. So we can actually transform it back into what we saw at the very start, which is, a single node and then everything else beneath it free. I don't know if that made any sense, but that's basically where my head's at. And that's kind of what we have to do. The only reason I did all that is because I want to make sure the positioning stuff makes sense, but I don't know if it made sense. But yeah, that's basically the gist of it. And if it didn't make sense, I'd recommend reading the chapter. It's a good chapter. I just try to go through it quickly and it kind of backfired. But yeah, so that's kind of what we're going to be doing today. I do have the notes, I do have the actual chapter printed out because there were some snippets of code that I think will be useful for me, that I would probably copy and plagiarize. So that's fun. Yeah, I think that's pretty much all. There's also all this stuff, but that's fine. We'll get to that when we get to that. We have to do some structural things first. So, I need to put this away. Okay. So we have our boilerplate. I also made a little macro just to convert kibibytes into regular bytes, just doing a 1024 times x thing. Hopefully, I think that works. Yeah, I tested it with a print statement before, so I think I should be fine. How do I do this? So what I need, first of all, is a region of memory. So this is where the mmap stuff comes in. So I think I can check this, man mmap. I think it's standard library. I am wrong. So yeah, so basically it takes in, it takes in a size, how many bytes you want, kind of similar to malloc. It takes in some protection flags, like, are you allowed to read? Are you allowed to write? It takes in some other flags. I don't really know what these do, but it takes in some file descriptor and it takes in an offset. So looking through this, the address argument is used by the system to determine if the starting address of the mapping, determine the starting address of the mapping. Okay, so there's like some stuff, basically looking at the chapter itself, what they write is something like this. They say, mmap null, oh my god, null. So that first void star doesn't seem to mean anything. And then they take, hold up. Oh, they do 4 kibibytes, not 16. Yeah, okay, maybe I'll keep it 16 then. It's fine. It doesn't make a difference. So basically, mmap, if I find the thing, there it is. Yeah, it takes in some pointer, but it's used as null. It takes in a size, so we'll say kib2 bytes. We'll say 16 kibibytes. Basically, some protection flags. You can read and write, but you can't execute. That's fair enough. And we're ORing it because we want both. And then there's some random other flags. I don't know what this is, but I trust the snippet. Private -1 for the file descriptor and 0 for the offset. So this returns a pointer. I'll say, can I say void star right now? I don't think I can, right? Does that work? Oh, it does work. I should have known that. Anyway, this won't be void star forever, but just to try and clarify what mmap does. Basically, it's kind of like a malloc, except we're not relying on the C code, we're relying on the actual operating system. This is a system call. We're making a direct communication with the operating system, as opposed to like using a function call to then do it for us. But yeah, basically, in other words, we're basically getting access to 16 kibibytes worth of memory, if nothing else. Okay, now we should make our structs. So struct, type def, sorry, type def. Struct, so we'll do the node int size and wait, I don't know if I can struct type struct node t struct node t star next. Wait, if I do type def up here, I messed up. I forgot the word struct. If I do that, can I do this? I forget. I think I can, right? Because this is declared. Yeah, it should be fine. Okay, so that's our first thing. This is going to be the structure we use for each free list node. And then if we have struct, what was the other thing I was talking about? Headers. Int size and int magic. In fact, can these be like usize? I mean, not usize, uint. Is this not a thing? Do I have to do it like that? Oh, okay, I'll keep it as int. I'm not that fussed. Yeah, if I do that and then do this. Okay, so we have that and that. So this is going to be the structure keeps track of the size of allocated regions placed in the heap right before the allocated region. That's what this is for, and this guy is keeps track of the size of an unallocated chunk placed in the heap right before this unallocated chunk. That's the point of node t. Okay, so we got our two structures. And yeah, this guy is going to be a pointer to a node t. Right? The head is going to be the head of the linked list. So it's going to be a node t pointer. Head size, right, is going to be the size of our thing minus the size of one node t. Remember, we're basically initializing what we had at the start here. So, you know, this is the header, basically. This is what we're creating right now. The size value should be however much memory is currently present in the whole heap minus the amount of memory required to make this header, right? Like however much is left over is how much we can use as free memory. Okay? I think. Yeah, I think that's right. And then there was something else. I want to make a function to return... Ooh, do I want to do that? Maybe I don't. I don't know. It's weird because I'm not using malloc or free for this, so I don't know how it works. Anyway. And head next is null. Good to always explicitly say. I don't know how it works otherwise. Okay, so we have this. We have kind of the initial state. From there, we need to define and design the kind of allocation function and the freeing function. And we have to define and design the splitting operation and the coalescing merging operation. So we should do that now. So let's begin by trying to allocate stuff, because I feel like, you know, you can't free anything, you haven't allocated anything. So we're going to do like, you know, allocate function, and we're going to do a splitting function. I don't know if we, yeah, I think it's good to encapsulate this in as a separate thing. Now, what's it going to need? Allocate is going to require a number of bytes kind of input, similar to malloc. You're going to need to be able to say, I want this number of bytes. And it's probably going to return void star, I assume? Malloc returns a void star, right? So I feel like that's fine for me. Yeah, void star. They do use size t, which is probably better. Should this be size t? Did they do size t? They did not, but maybe I should. Size t is like unsigned, right? What the heck? Unsigned long, yeah. Ooh, but long is tricky because isn't that 8 bytes? So that might screw me up. Maybe I'll keep it. Keep it as integer. Don't get too excited. Ooh, wait. This is going to be 12 bytes, isn't it? Because I've got a 64-bit machine. This book I think was written before, in the past. Like not olden times, but oldish times where 32 bits were more common. So if this is 12 bytes and this is maybe I'll make the magic number. I just feel like I should make these two the same size. I don't think they have to be, but I just think for my own just peace of mind, I think it's good to have that condition. Long is 8 bytes really, right? On Windows and 32-bit systems, yeah. So I'll do that as, I'll say that. Oh, that's weird. Anyway, it doesn't matter. So we're actually going to be using 12 bytes for the structures because 8 plus 4. I did not think of that. Okay, so we have this idea. If I decided to try to do an allocation function, then what? I hardly have to take in the head, right? Like the start of the linked list, as you would. And, there are various strategies to determining, like, which node to use, if any is available. There's like these 4, which are like the introductory ones. There's others as well, but these 4 are kind of probably the easiest ones to talk about. What I will probably do is the first one. No, I'll do this third one. First fit. Basically, from the start of the linked list is a pretty sort of naive approach. From the start of the linked list, you iterate through and you find the first node that accommodates the request. So, you'll have like a bunch of node T's. They will have certain size values, right? Certain size values, and you pick the one with a size value that is at least the size of num bytes. And if it's greater than num bytes, you'll do a split operation as well, right? But yeah. So we'll do first fit. Just iterate through, find the first one that works. So node T star current is equal to the head. I can do this as a for loop, right? For node T star current equals head. Current is not null. Current equals current next. That's fine. So we iterate through. If current size is at least the size of num bytes, then we should do a kind of split operation, I guess. I should keep track of the actual start of the thing, right? Now I'm getting confused. Do I have to cast? So what I'm trying to do is like basically have an instance where I'm actually able to keep track of the start of the. Maybe I don't need it. I don't know. Anyway. Okay, so we're iterating through the nodes. When we find the one that is good, we're going to basically transform it into a header instead of a node. Same size, so it shouldn't cause any weird stuff. Yeah. And then we're going to say, what are we going to say? We're going to say the memory that you take how much memory you can, and the memory after it becomes a new node. Okay, I need to draw this because I'm trying to do this in my head and it's not working. So let's say you have some region of the heap, looks like this, and you have a node T, right? Part of the free list that looks like this, has a size associated with it. This is the size, and then it has a next pointing somewhere down the line. Let's say the request comes in for some bytes, and this particular node is the first one that accommodates for that allocation. Then this will become a header telling us how many bytes have been allocated. I'm coloring it green to indicate that. The bytes will be allocated, and a new node has to be placed just past the allocated region. This becomes a new node with the associated free memory just beneath it. So originally this entire thing from here to here, or maybe even here to here, or whatever, right? The entire thing was free with a node associated with it. So the steps were, this became a header, a certain region of memory got allocated, beneath it was the next header, a new header that I colored in blue, and then that's it. Okay, so change it, make a new node, basically, are the two actual operations. Change this, make a new node. That making the new node is kind of the split. This is just like always going to happen, and then so assuming there's space available, this becomes a new header. And if there's not space available, then I think we just won't do that. We'll just allocate all the memory. We'll just give all the memory to that allocation, as opposed to trying to put a new header in. Putting a new node in. Sorry, I don't know if I've been saying it wrong. I'll talk about that more in a second. But for now, if this is big enough, then what do I do? How do I actually... Ooh, the other thing is, when I'm basically deleting a node when I replace it, right? So I need a previous as well. Can I be like node T previous equals null? Does that not work? Wait, I swear you can do something like this where you assign two variables. No? Okay, hang on, I've forgotten my C. How to define or declare two variables in a for loop in C. What did I do? Wait, what? It has to be the same type, so they don't put that. Okay, fair enough. What? What's wrong with that? A type void star cannot be used to initialize an entity of node T. Oh, the star is associated with the variable, so I have to say star here as well. Is that right? That's annoying. I didn't realize that. What if I put it in brackets? Is that helpful? No. I guess it's like a cast almost, which doesn't make sense. Ooh, I don't like having the star on the variable. That's really weird. Anyway, that's fine. Okay, well, for the love of the game. And this happens, and also, but before that happens, previous should become current, just so that it always... I am nervous. What if the very, very first one is... Okay, so... Okay, in the case where, we found we found the memory region that we want to use. If previous is not null, so it's not the first one, like we didn't use the very first node to do this. If it's not null, then previous next I think should equal current next. We're basically skipping over current is what we're doing, right? Nice and simple. So it's skipping over it. We're maintaining the free list. But we might be inserting a new node. Maybe I don't need to do that. I don't know. I'm just confused. We'll have to definitely redirect previous next somewhere. It's just if we're creating a new node as well, then it might not be to current next. That's what I'm saying. Might not do this yet. Okay. What we do definitely need to do is probably note down the next. Note t star next equals current next, just so we have it. Because if we lose it when we reassign current, then like when we swap current with a header, we might be in trouble. If I do header, if I say header t star current, does that work? No? I casted wrong, hang on. No. How do I do, like, make it a header? Like, I want to use the exact same region of memory. I just want to make it I want to give it header fields instead of node fields. What if I do header t star new header equals, and I literally just cast. I messed up. See, there the star goes on the type. I prefer that. New header size is equal to the current size. Okay, so I should probably save the size as well. Int current size is equal to current size equals current size. So what the size, ooh, that's wrong. Hang on, that's not right at all. It's the num bytes that are requested. I feel like that could blow up as well on me actually, but I'm scared. So yeah, we keep track of the next, we create a new header, we give the size, and the magic number I'll just define. So like I said, the magic, it's like a random, that's fine, right? That's like not a billion. 1, 2, 3, 4, 5, 6. Yeah, it's like 23 million. Okay, that's fine. New header magic equals the magic header number thing. Magic number. Yeah, that magic field is like, as far as I can tell from the book, is just a way of making sure that you have a header and not just some random garbage. Like if the magic number equals this number, then the chances of it being garbage, like just random thing that isn't what you want, is like very low. So should be fine. If this is this, then do this, and then do this, and then, yeah. And then what? I now need to make a new, okay, so this is my concern, right? What happens if your remaining bytes, like, because you got to remember that you have a node in blue with some associated memory, and then you have maybe some other node or whatever, or maybe some free stuff or whatever. But you have some this sort of border of free memory that your node, sorry, I keep saying header and node interchangeably, that your node is associated with, right? When this becomes a header, all right, when this becomes a header and you allocate some of that memory, this is now allocated memory. The question becomes, is what's remaining enough to store both a header and some free memory, right? What's remaining? Because if this is, 20 bytes, then yeah, we can put a header in here, all right, which is 8 bytes worth, and then this will be 12 bytes, right? 12 bytes of free memory. But if this region here is like 4 bytes, we can't fit an 8-byte header. We can't fit a blue thing. The blue thing will spill over the 4 bytes, right? We can't fit, did I say header again? Node, I meant to say node. We can't fit a node in here to describe the free memory anymore, because there's not enough free memory to actually store a node in here. So we have to actually check if this guy in here, after we do our red allocation, is this guy in here enough to store a node? A node. If, so we've put a header in here. If the size, I do need the size, hang on. Int current size equals current size. If current size minus numbytes, we already know that current size is bigger than numbytes, or at least the same. If that is at more than, has to be more than. There's no point putting a header if there's no more memory after that. If it's strictly more than the size of a node T, then we can very happily go past the allocated red part and put a new header in here. Node T star new node. Just Alan, just give the memory for it first. If current size numbytes is greater than size of node T, how do I get to the end of the red region? Where am I? I know I'm like here, right? Like header T, new header is the start of the green. So I add this. I add the size of, I'm really concerned. I don't think I know how to do a pointer arithmetic well. I need to add 8 bytes and then add the number of bytes that were allocated. And that should get me the address of the next spot, basically. I'm just concerned because when you do pointer arithmetic, it adds on the number of bytes. Like if you add to an integer pointer, when you do +1, you're actually adding 4 bytes. You know, like it's like that. So I don't know if I'm gonna actually be doing this correctly. Maybe it's like, hang on. What if I do void star new header plus the size of header T, right? Thereby adding on the 12 bytes, it's 12 bytes. Adding on the 12 bytes, and then I add the number of bytes that were allocated, and this should give me next node location, I think. Can I just check? Pointer arithmetic on void star pointer. Does the address go up by 1 when you add 1? Oh. Okay. Well, that's awkward. How do I get around that then? Char star? Can I do that? Char star? Because then it's 1 byte kind of thing. I might even type def char byte. And then be like byte star. It's like a byte pointer. Byte star. I mean, I just need the pointers, man. Next node location, new header size. So from the new header, we add on the size of the header to get past the header, and then we add on the size number of bytes that were allocated to get past that red region, and then we'll be right past it into the spot of the new thing. So then, can I say, if I say, oh, I'm confused. If I say this is a node T star, is that fine? And I just say next node here. Or even new node. Because I have next node, don't I? I have next. So, yeah, like if I if current size, if that free region's current size minus the number of bytes that were allocated is bigger than the size of a node T, then let me get the new node's location. I think this is valid. I'm not 100,000,000% certain, but I think this will do pointer arithmetic where +1 adds 1 byte to the address, I think. Because I'm using this type, and like when it evaluates it, it'll be like, oh, this is a char star, so add 1 kind of thing. New node size is equal to, what is the size? It's going to be how big this guy was, current size, minus how many bytes were allocated, and also minus the size of a header T. Because we're saying the blue, like the really thick blue, was the original free memory. We allocated a red amount, which is the num bytes, and also we are using the, ignore the 4, we're using some of the bytes to make a new header in here. Right? So we have to subtract the red and the blue, where the blue is the new header. So subtract that and that, red and blue. Red and blue. So the new node size is that, and the new node next is equal to the next node that current was once having ownership of. Now, if there is enough space to put a new header in, then what I'll do is I'll say new header size, instead of making it equal to num bytes, I'll make it equal to the total size of the chunk, the current size, what that current node was, like how big that free region was, the total thing. I might as well just allocate all of it, because I'm not going to put a header in there. There's not going to be free memory I can reference, so I might as well just make it part of the allocation, just so that it's not something random. Okay, so I think that makes sense. I was going to do something else. I forgot what it was. I've done that. What was it? I had to do something. Yeah. I have to check if previous was null. This is getting quite ugly, but it's all right. If previous was a thing, that means that previous is next should equal to this new node. If previous is null, right, then we're in the case where the very first current, the actual head, was big enough to handle the allocation, in which case the head pointer should now point to the new node, because the new node is the head, right? Because the current node we used in this case, where the previous is null, the current node we used was actually the head node. So the head node is gone. We have to redirect the head pointer to point somewhere else, to the new node specifically. So hopefully that keeps the order of the linked list correct. I'm hoping that's the idea. But yeah. Okay. So I didn't really write the split function, but I can do that because I feel like the split kind of happened in here, where you kind of made a little chunk and stuff. Hang on, wait. This still requires this. If previous is a thing, then previous next equals the next node. What current's next was, if we never created a new node because, we couldn't, then previous should point to next. And else head should equal next. Because, again, it means that it means that the current was the head. So now that's been replaced by a header T, head needs to point somewhere else. The head of the free list has to point to the next node. That's the next top address or whatever. Okay, ugly function, but hopefully written somewhat correctly. Probably not by knowing me though. Like I feel like this could probably be a function, like splitting. So what? Given the node T star, given the position of that node, given, I guess I need num bytes as well. New header. Ah, right. Hang on. I don't have a node. I don't have a current node anymore because I turned it into a new header instead. Header T star, the new header, the number of bytes, and something else, and I'll just write the body, and then whatever errors happen. I want to say int the free region size, right? That's like the current size, like that. I want that. I want the number of bytes allocated. Do I want anything else? Next node. Sure, I can take that. Next node T star next node. We good? All right, and then return, I guess, this new node. At least it's something, huh? Some kind of encapsulation. What have I done? I lost my train of thought because of reasons. Node T star new node equals this, I assume. And then get rid of all the types. No int. Whoa, didn't mean to do that. And then free region size is not free region size, it's current size. And number of bytes allocked. It's num bytes. Maybe I prefer number of bytes allocked. It's a bit longer, but maybe clearer. What? Give me the thing. What? Why is the thing not working? I swear. Oh, okay, sorry. Why is this wrong? A value of type void cannot be used to initialize. That's fair enough. This is not meant to be void. This is meant to be header. Nope. Node T star. Okay, is this correct at all? I have no idea, but here we are. So we've done a bit of a split, and we have checked if previous. This is like very similar code, so I think if we do something like void, like redirect, like redirect the linked list kind of thing. Node T star the previous one, node T star the middle one, node T star the next one, node T star the, that was kind. Does this make sense? So if the previous exists, just trying to see if I can do the same thing twice. Previous next is equal to the middle guy. node t star head. I think I want that. Else head is equal to the middle guy. Does that work for this as well? Previous is equal to next, head is equal to next. Yeah, so like new node is middle here, whereas middle is next node is middle in this case. Right, so instead of doing all this, I can say, and then we can return head. We can say head is equal to redirect the linked list given previous is the previous, the middle is the new node here, and the next is the next node, and the head is the head. What's wrong with that? Oh, I've done it again. Node t star. Then here, does it work? I'm not 100% sure. Head is equal to redirect the linked list. Previous is previous. Middle next is just, do I even use next here? I don't, so I don't even need that. So instead of calling it middle, I could call it next. Oh, it didn't work. How do I, yeah, okay, that's one way to do it, I guess. You know, this one and head. I don't like the name redirect linked list. Like, you know, insert, I guess. Yeah, insert. Insert is fine. Insert node. Yeah, that makes sense. Given a previous and given the node you want to insert. Maybe I should call this new node. Should I say the new node first and the previous after? Does that make more sense? What am I doing? That's the wrong function. But you're not really inserting for the next. Oh god, I'm getting done in by my naming. You're not really inserting here. You're just making. Let me undo. Hang on. I'm getting stuck on the wrong thing, but. Point prev to next. It's as accurate as I can make it. Whoa, didn't mean to do that. Okay, we're pointing previous to next. And possibly, if previous is not a thing, then we'll make next the head. Okay, so in this, wait, this new node, did I make next? Okay, I didn't. Okay, good. Okay, so that's us trying to allocate memory, basically. On the flip side, if we want to free memory, right, which is a void function that takes in a pointer and nothing else. Wait, why is this here? Allocate shouldn't have the head associated with it, right? Should these be like globals? I'm not generally one to have globals, but oh, of course, yeah. Wait, what? Okay. Okay. guess it's going to have to take in the head as well, or no? Maybe not. Maybe yes. Because I have to coalesce, and I feel like it's going to be hard for me to do that if I don't have this access to the actual free list. Okay. Step one, though, is we have to look at the header. So, header T star associated header is equal to, it would be, can I say header T star pointer -1? That should shift it back 1 and actually get me to point to the thing, right? Assert, is assert a thing? Wait, is assert not a thing? It's a macro. Do I have to, okay. So yeah, you're supposed to just, it's supposed to be a given that the, what do I call it? Associated header. The magic number should equal this value. This should be a given. Like, this should never fail. And if it does, it's something like you've done something proper dumb, kind of thing. Which is why that's like the major point of this magic field, is just to give a bit of sense of security and like a sense of assurance. Okay, so we do that, and then we say associated header. So int region size is equal to region size is equal to the associated header size. And then what do? We say node T star new node is going to equal it's going to equal node T star of this associated header. Yes, because we're replacing it back. We're doing the reverse. We're taking header and turning it into a node. New node size is going to be equal to the size of the region, however much memory we manage to free. Now the tricky part is actually finding where this guy's next points and who should point to this guy. You know, are you the head? Are you do you have the smallest address associated with you, or what? Can you you should be able to compare pointer values in C. Such as an array or a struct. Ooh, is that legal? Hopefully. Don't know if this is going to be a problem. Right. Okay. I think I'm okay, because it's all within the M map, so it should be okay, hopefully. Same kind of for loop, I think. Did I copy? Hope I did. Okay. So you start at the head of the free list, give a previous value, you terminate when current becomes null. Yeah, so while current's not null, wait, hold up. Yeah, so I forgot how for loops worked for a second. You assign previous to current and you make current go to next so that your continuously incrementing them across. What am I trying to do? If like the actual address that current is at or rather, hang on, if the new node has an address that's less than the current, then I think I found the thing I want. I think I found it. I think I found the spot, right? I've incremented down my heap or whatever. Like I've gone up and up and up until I found the first current that is at an address that is bigger, like value-wise, is bigger than the new node that I'm trying to insert. In which case, I should insert here. Does my function still work? Point previous to next. Given that my previous should point to the new node, and my head looks like this. And new node should probably point to current, right? So I've definitely hit both fields. I've made the next point to the right place, and I've made the size value the value it should be, hopefully. So the previous will point to the next, and if previous is null, then the head will actually be next, hopefully. And then, assuming all that works, I guess I can break out. Like after I do this if statement, because like I found the place to insert it. There's no need to keep going. So I've done that, and then I have to do a coalesce thing. Right. Well, assuming like coalesced memory is like an invariant, like before I do this insertion here, we can assume the memory is completely coalesced. The only place to do the coalesce would be where? Between the previous, the current, and the previous, the new, and the current, right? Like only between those three could there be some coalescing going on, I think. How do I check if it's adjacent? Okay, yeah, you go through this. If you find it, you point this, and then you have to coalesce. So I think, I could be wrong. I'm basing this off like logic, but I don't know if the logic is actually correct. I think the only place, assuming the memory going into this function is already coalesced, like it's, there's no random breaks when they don't need to be. The only places where you might have to do any coalescing is between the previous and the new, right? Previous and the new. New and the current. No. Yeah, new and the current, which is kind of acting as our next in this case. So that's the only places where the coalescing might have to happen. If that happens, will something bad happen? I think we just have to jump. I think it's fine. I think so long as we... Oh my god. Okay, hang on. Okay, yeah. Okay, if I make a... So I'll split and I need a coalesce function. So, I don't even know. Node, I guess? Or header? Yeah, node t star coalesce. Is that how you spell coalesce? Guess not. 1L. My bad. I guess, yeah, given my previous, given my sort of middle guy, and given my next guy. So the possible points of merging are between previous and middle and next. There's kind of some weird cases, like previous could be null, potentially, in which case I've got to be careful. If previous and it's weird. Hang on. How do I do this? Let me try and go through the cases. So like either we have 3 legitimate chunks, right, with headers to describe them, right, which I'll color in blue. So like this is the header for this chunk, and this is the header for this chunk, and this is the header for this chunk. This is my previous, current, and next, or whatever. And they're currently 3 separate headers, but they could all just go. Oh, I've broken everything. Hang on. But they could all go under one header. Which would also free up some space, right? Like we wouldn't need these guys anymore. So it would also save like 12 bytes plus 12 bytes kind of thing. But yeah, so I don't even know what I'm doing. If previous and I should probably write a function just to be like are these 2 headers are these 2 nodes like representing chunks that are contiguous, like adjacent? Free regions are contiguous given region 1 I'll say left and right. I feel like region 1, region 2 can lead to typos. I don't know. Bottom and top. Top and bottom. So if I want to check that this header and this node and this node represent regions that are adjacent, I basically want to check if this address, if I take, like, this will have a size associated with it, right? If I take this address, add on the size of the header, and then add on the field, it should equal the address of this header. So I'm saying return top plus size of node T plus top size should equal bottom. But see, once again, I think I'm messing up because I feel like I'm messing up because this is going to add way more than what I want, right? Like, this is going to add not like this is going to, it's not going to treat this as bytes. This is going to treat this as a node T star, which means it's going to add like, because this is what, 12. This is going to add 12 times node T star. You know, like it's not going to be right, I feel. I think I have to make this into byte star first. Whoops. And then do this addition, and then it'll be fine. Equals bottom, and I think then the pointer arithmetic is fine. I don't know. I feel like in places I've done it badly. I have to look at it again. Why did I put this function up here? That's a bit random. If previous and free regions are contiguous between previous and middle, then we should coalesce the previous and the middle, which means previous previous size is equal to previous size plus size of node T plus middle size. I think this is right. Basically what I'm saying is, you know, if we focus on the, you know, this, we focus on this guy and this guy as our two regions, you know, this has a size field, as does this one, which corresponds to the size of this region and the size of this region. When I merge these two guys together, how many bytes is associated with this header now? Well, it's this red plus this red plus this header as well. So that's where I get previous size, middle size, that's the two reds, plus that middle node as well. I might have said header again. Anyway. I wonder if it pays to go backwards. If middle and next and free regions are contiguous between middle and next as the top and bottom, then middle size is equal to middle size plus the size of, size of node T plus the next size. I wonder if it's better to call it top, middle, bottom. I feel like I'm visualizing it better when I call it like that, like to compare it to like this kind of diagram. The reason why I think this is a good idea is because it kind of carries backwards. Like going backwards means, you know, first we check if we can combine middle and bottom together to make kind of merge these two guys together. And then we check if we can merge these two guys together, you know, because if we can't, like, I think that's the best way of doing it. You know, if we can merge these two guys together, then we will basically get rid of this header and associate this massive block down here with the size field in this header, in this node over here. And then and only then do we try to merge the top with the middle, which will either be, you know, just this guy by himself if we couldn't merge couldn't merge the bottom, or it will be this entire block here if we could merge the bottom. So I think going backwards is actually the clever way of doing this. If top and middle, I don't know, I feel like I should just make sure that none of these are null, just to, you know, be sure. And then in terms of, I was thinking of returning something, but maybe I don't have to do that. Maybe it's fine just to say void. So yeah, we just got to do a quick coalesce between the top, the middle, and the bottom, which is actually current. Okay. I don't really know how to test this, but I can do my best. So we kind of have a heap, quote unquote heap going, and then yeah, I guess let's say I want to allocate 200 bytes Does this return anything? No, right? Oh, it returns the pointer. Okay, hang on. Void star pointer 1. Void star pointer 2. 500. Well, I have a question. If head is getting assigned to different things, right? This is just supposed to return a pointer, by the way. I forgot to do that. So I have to return the pointer to the new region. which will be where the header is. Which will be where the header is. Return new header +1. We're going to add one header's worth to get the address of the region or whatever. I'm not really sure how to make sure this doesn't spill into like past the allocated region, but I'm sure that's someone else's job. I think this is right. +1, because I'm adding one header's worth of bytes to this pointer to move past it, to move past the header. That sounds about right. Where else did I do like proper, like here looks like actual free region size is this is all integers though, so it should be fine. This looks like, okay, but I use the byte star, so it should be fine. New header, add the header size, and then add the number of bytes to allocate, yeah. And then that's where the new node would go when you're doing the split. Yeah, okay, I think that's fine. Space here. Did I do anything cool or what up? I should probably make a function just to print like what the heap looks like or something. Void print the free list, I guess, given for node t star current equals head current is not null. Current equals current next. Is that fine? Okay. The address, whoops. The address. Maybe I won't put a new line. Maybe I'll just put an arrow. And then I'll say current percentage %p. Is that a good idea, or is that going to be really dumb? And then current size. And then print f and x at the end to represent the null connection. Would it be better to try print like the actual heap, like the entire thing? Is that dumb or? Ooh, we'll say byte star. Was that dumb? Ooh, I don't know. It's gonna be really, because we don't know what's actually in the heap. Is it a node t star? Is it a header t star? Is it just random free stuff or whatever? It's gonna be really tricky to print that, I think. So maybe I'll leave that for now. Hopefully printing the free list will give us a good enough idea as to whether I've done this correctly. Now, I will say, I don't think, like, the head sometimes gets reassigned, right? Like when you're freeing, point previous to next, yeah, head can be reassigned. That's the idea, like it returns head, so you need to reassign it. So in that kind of way, I'm wondering if it's smart to actually sort of take in a double pointer so that the reassignments get fed back to the caller. Ampersand. I think that's how that works. And same kind of vibes here. Yeah, like free has a reassignment of head, and allocate also will have some like that and that. So in that way, like those reassignments, first of all, should be dereferences because of reasons. Yeah, I feel a lot better about that. That makes more sense. I remember I used to have bugs like where I wouldn't do a double pointer and then try to do reassignments, and then they wouldn't be fed back to the caller, and then I would be sad. I think this is better, hopefully. So yeah, let's like do void star pointer 3 equals allocate 1,000 bytes. Is that too many zeros? Yes, it is. Given this guy, and then let's print the heap again. So this should like basically just put in like three headers, and then like 3 headers, and then one node basically that keeps getting pushed down the heap, and then so void star, and then if I say free, did I call it free? I should probably call it like not just free. I mean, I guess I didn't put in standard lib, right? So that won't be a collision, or will there be? Because free is the actual function name of the actual thing, so I'll call it my free just to make sure, just to play it safe. My free given the pointer, we'll say pointer 2 first, and the heap, I assume. Oh, sorry, the head. And then we'll print again. And then we'll free, let's say, 1. I think that'll make the coalescing a bit more interesting, hopefully. Yeah. And then my free. Alright, how many bugs do I have? Well, I don't think this is going to compile at all, to be fair, but... Bang. Wow. Warnings. Incompatible pointer types with initialization. Oh, I have to cast it completely. Yeah, I figured that stuff like this would happen. So you first do all that, giving you a byte star, and then you cast the entire thing as a node T star. I'm assuming this is the same kind of vibes. Wait, what? Node T star. Ah, of course, because I have to dereference. Yes, it's good to keep this selected. And this will have to be dereferenced as well, probably. Actually, yeah, I'm returning head here, so that's fine. That gets communicated back, that's fine. But yeah, it does mean I have to dereference in places. Here as well. Same vibes here, got a dereference, got a dereference. And that should be okay. Yeah? Just handling just double pointer handling. Non-void function doesn't return all the time. That's annoying. Ooh, okay, so yeah, what happens if I run through this whole thing and I never hit the if statement? Return null, I guess. That's kind of what the actual malloc does, right? Returns null if it doesn't work. And I'll just make a function like void check allocate worked given if not pointer. Alright, and then yeah, if it doesn't work, then I think I'll very quickly segfault because I'll try to dereference a thingy. Okay, apparently I said allocated somewhere. That's hilarious. I did mean allocate. Good job. Incompatible integer to pointer conversion, initializing void star with an expression of type int. Pointer 3 equals allocate. Ah, it's because I sponsored off. Comparison of this one versus, yeah, okay, I thought that would be a problem. I wasn't sure. Yeah, I can make you a byte star. For sure. What am I doing? Okay, that kind of failed completely. Well, not didn't fail, it's very long. Okay, maybe I will put a new line like that. And like, whoops, and like that. Or is it better to have the arrow like at the start? No, it's easier to do it like this, isn't it? I did not compile. What am I doing? Clang. There you go. All right, let us check this out. So I will also do a double \n just so that I can really keep things separate. All right, nice and slow because of how many linear allocations, like linear operations there are. Okay, so we begin with 16152. I think the numbers there should match the numbers here. Do I have the numbers written down? I guess I can figure it out. It's just annoying. Oh, actually, I did random allocation. So yeah, let me get rid of all this. Let me see if I can figure this out. So the memory looks like this. 16 kibibytes total. So this address up here is 0, and this address past the memory is 16 KIB, which again is... What? Why am I on the apps? What? Whoa, when did I ask for that? 16384. So this region is from 0 to 16383. 383. 384 is like just past it, the next address. Okay, so we have all this one, and then what do? I do an allocation of 200. So if the header is originally like this, in fact, let me do this one more time. Let me first print the free list before we even do any allocations. That would be probably a good idea. So I'll just, yeah, so it starts by going like this. It's 12 bytes. So 0 to 11 should be the thing. 0 to 11 should be the header, the node, sorry, and then 12 to the end here should be the free space. Oh, it's hexadecimal. I suck at hexadecimal. Okay, well, apparently in this case, the address of the node is this guy, 102D98000. I'm gonna suck at this. Is this 200 by any chance? Or something? Is it close to 200? Can I, hang on. Can I print, oh, my mouse is going crazy. Can I print memory addresses in regular decimal instead of hexadecimal in C? Surely, like, come on, sometimes in life, fine. To print it using an unsigned decimal integer without causing compiler warnings, you must cast it to an integer type large enough to hold it. Okay. Guess I'll take these two guys. What the heck? What the heck is even that? If you're working on a system where pointers fit into standard types, use long, long unsigned. Yeah, fair. Yeah, that makes sense. Okay, I guess I can just try that, just to try keep things from being too complicated. So, where's my printing function? So at the bottom, should be, right? Print the free list, yeah. So instead of %p, we cast this as a long, long and then hopefully nothing bad happens. Okay, cool. So the address, the starting address in this particular instance, like I was using 0, but the fact is it's not necessarily 0, right? So the starting address is that, which means, okay, when I do the allocation 200, what should happen is, where's my pen? There it is. When I do the allocation, what should happen is that first header, that first node, sorry, becomes a header. So I have header, also 0 to 12 by design. I then have 200 bytes of allocated memory, going from 12 to 212, not inclusive, so inclusive to exclusive. That's like that. And then I should have a node, right? Free list node, don't shade it, color it, from 212 to 220. So since the actual start is this number here, which is kind of like a magic number, the actual memory address should be 212 plus that number. Is it? 43? Oh, no, it's not. Oh. What was the size? What was the size? Well, if this guy is 16384, then the amount of bytes is the difference, right? 16384 minus 220 is 16164. Nah. Was it correct at the start? 16368? Should be, right? Like, wait, hang on. 16368? 16384. Ah, but you got rid of 12 bytes. 16384 minus 12. 372. What? How did I mess up at the start? Size of the node? Print. I do rely on the size field, right? Yeah, I do. Something appears to have blown up in my face. I would assume it's some kind of pointer arithmetic type thing, but I'm not 100% certain. I also probably didn't need to do the heap thing. I don't think I actually ever use it, so I'll get rid of it for now. It's just a random variable I didn't end up using. The size is this thing minus this thing. Let me just confirm a couple of things. Diagnostics. Right? Printf, I need a semicolon. Printf, head size maybe I should wrap this in brackets or something. No, but I already wrapped it in. I wrapped the macro in brackets in there, yeah, so that's not going to cause a problem. I trust the macro. head size let me just check this. Also, let me check size of node T equals size of node T. Oh, my bad. What? Oh, sorry, I didn't say my bad. Okay. Should have put another new line in there, but 16. Ah, it's 16 bytes. Is that because I messed something up, or? Wait, can things not be 12 bytes if I align them correctly? I guess not, because of the... Alright. Long it is. 16 bytes. Okay, so that changes things a little bit in terms of raw calculation. Ah, of course. That messes everything up, doesn't it? LD. LD. We're good? Okay, it's 16 bytes. I think the memory alignment, because it's a 64-bit machine, what does that mean? The boundaries or whatever, the word boundaries are 8 bytes. So if you use 12 bytes, it will use 4 bytes of padding. I forgot about that. My theory is bad, see? But there you go. Okay, that's probably why the numbers are messed up. Hang on, let me try this one more time. So instead of 12, it's 16. This number I would still think is the same, but hopefully 16 384 minus 16 gives me 16368, which hopefully is the, okay. So the first state is good. At least that's printing correctly. From there, we do this whole. Oh, the number would have changed because it's a random allocation. Okay. From there, so yeah, this is 16. When we add 200, it will become. Does that mean these numbers aren't going to... I don't know. I'm worried now that... Is the alignment going to mean that I can't... Probably not. It'll be fine. So this and then 232. So from 216 to 232 is that header. And then the rest of it's free. So the node I should see, I think, is... The blue node should start at address 4,301,000,000. Oh, 258. Oh, 96. Oh shit. Yeah, I probably shouldn't have gotten so excited. What's the discrepancy there? So this number, which seems to be bigger than what I wanted, off by 16 bytes. I don't know if that's because it's off by like one. It's off by one shift. You know? Why has that happened? Is my maths wrong, or is it? I am correct in saying that going from 0 to 16 is the first header, and then the red would go 200 bytes, assuming this is right. And then 232. Is this divisible by 16? Or by... Four bytes, 16 bytes. 4 bytes, 8. Is this divisible by 8? It is. But not divisible by 16. Okay, so that shouldn't... Yeah, that should be fine then, right? Oh, I'm scared. Like, I think they're very nice round numbers. I didn't put weird numbers in, so I'd be very sad if this didn't work. Address 43012. So this was correct, and then where could this have gone wrong? Could it have been like something to do with the point arithmetic, or what could I have messed up? You have head, you have previous, current is null, previous equals current, current equals current. So you're moving across through the for loop, you're moving through the list. As soon as you find one that's big enough, and in the very first case, it will be this header, there's only one, and it's going to be big enough. You get the next node, which is null in this case, and you get current size, which is this guy. This guy. New header, you take this guy and you transform him into a header T star. The size of the new header is the number of bytes that got allocated. Ooh, wait. Should that necessarily be... Because there are cases where... Oh no, I counted for that. Sorry, I forgot I wrote this line. Okay, that's fine. So yeah, it's the number of bytes allocated, and the magic is the magic header. Good thing is it doesn't seem like that broke anyway, so that's good. If you have enough bytes left over, if the current size of that node, if there's enough left over to create another node, you do a split where you basically assign the new node by going the new header, size of header T, number of bytes alloced. Okay, let me just get rid of my test besides just that first allocation, just so I know what I'm doing. The free region size minus the number of bytes allocated minus the size of this new header that we're going to be putting in as well. New node next equals next node. I have a question. When I print stuff, when I print a pointer with, it's LLU, right? Yeah, okay. But I have to cast it as well. Okay, wait, let me just check what happens. I just want to see what it looks like. In the split, position of this guy is this. So this didn't change from here to here. And if I take the difference between you and you, it's 216. So from the starting point... Oh, that's right. Wait, that's right. Wait, what? Did I mess up my math? Am I tripping out? The difference between this and this, the 888 versus the 672, is 216, which makes sense because you jumped 16 bytes and then you jumped the 200 bytes, and that's the next header. Wait, hold up. Did I just not do math correctly? Is that what I've done? All right, let me just add one more allocation. I didn't compile because I'm dumb. There we go. So this was the original. This is my starting position. Then the difference between this guy and this guy is 216. And the difference between this guy and this guy is 732. So I have to check that. So what happens? So after the second allocation, what happens is that first header is still there with the 200 bytes of allocated memory. Then this guy also became a header with 500 bytes. So 200, 200. Then you have a new node and some free memory. So the address of the node will be 16, 16, 200, and that should say 500. So 732, which is what we got. Good. Okay, so that does work. Yeah, I must have just must have just done math wrong, basically. And then this guy, I can predict it, right? It would be 200, 500, 500, sorry, 200, 500,000 plus like 3 16s, like plus 48 because of the 3 headers. So 700, 1,700, 1,748. Is that fair? So in that last... Is that what I said? I forgot. I think so, right? 1,700 and 48 for the 316s. Yeah, okay, I backed that. Now I want to see what happens when I try some freeing. So now we have two things, so I'll draw them out. So when you do the 1,000 allocation, oops, when you do the 1,000 allocation, it's 12:10. Okay, been going for like just over 2 hours. When you do the 1,000 allocation, similar pattern. You have this, and then a bit of this, and then you have another one, and a bit of this. That's 200 and 500, and then you have another green, and a chunky boy, but I won't draw it chunky because I didn't give enough space, and then your next header, and then the free memory there. When you do the free on pointer 2, which is this guy over here, the idea is the pointer points past the header. The pointer given by the user, the pointer we give to the user, should be past the header, which is why when I return from allocate, I return new header plus 1. I'm going 1 header's worth past header, like the pointer here plus 1, getting past it. So they give, pointer 2 would be this red guy here, this guy here. I then should go back, find the size, and realize that this entire guy from here to here should be freed. So if this is 0, then 0 plus 16, this is 216. So it should be 216 with a size of 500, basically. Like this should become a blue, right? It should become a node with the next pointing down to here, and its size should be 500, and its starting point should be 216 past the original address. So this guy, oops, didn't mean to do that. What the heck? Okay, this guy minus this guy. Crap, I copied instead of pasted. 216, right? So that makes sense. And then this guy down here should still be 200, 500, 100, 1,000, sorry, 16, 16, 16. So the same numbers before, 1,700 plus 48. Fantastic. Okay, so that's worked. Now the next free should cause some coalescing. So how should it look? I'll make a new one. It's very thin, hang on. So yeah, originally we have this, followed by a bit of this, followed by a blue, followed by a free thing, it's free, followed by a header, and 1,000 bytes, and then another blue, another node. So yeah, so this is allocated, as is this. 200, 1000. And then this would be 500, free. So when we free this header, it should tell us that, we go back 1 to look at the green, to look at the points, to figure out how many bytes have been allocated, 200. We turn this into a blue, and this becomes freed. This guy should point to here, who should then point to here. And then when we call coalesce, what should end up happening is this basically goes, and this next here should point all the way down to here. And the amount of memory associated with this blue up top should be 716. 700 because of the 200 plus 500, and then the 16 because of that extra node that we basically aren't using anymore. So the size should be 716. This should be at the starting point, 0. And then this guy should still be the 1748, I assume. 716 plus 1000 plus 16 plus 16, yeah. So let's quickly check that one. 216. Ooh. That's wrong, isn't it? Like I said, the size should be 716, right? Did I compile? Looks like I did. Hang on. Oh, actually, hang on. There should be another one of like this 2 size links list. I might not have compiled. Hang on. That looks a bit suspicious as well. Size 500. Yes. And then size 14620. Can I confirm that? 1000. So how many bytes are there total? 16384. And I subtract off 200, 500. I subtract off 1700. And I also subtract off 16, 16, 16, 16. 16 times 4. 14620. Okay, yeah, good. So that's how much memory is associated with this last free region. So what's happened here? It seems like the coalescing didn't happen, unfortunately. So let me just maybe put back the other blue, because it seems like maybe they haven't coalesced. This was 200 bytes worth. And this was 500 bytes worth. And this is 1000. 1000 bytes worth. And this was 1748. I was done with me drawing this. Hang on. 200, 500, and 1000. 200 free, 500 free. Is that what it looks like? So interestingly enough, this says 716, so I don't know where that's come from. Oh, wait, 716 means it knows... Okay, so I haven't actually cut out the middleman yet, because I got 716 correctly. What is this address referring to? Minus the starting address? Yeah, okay, so it did that correctly. It actually merged it correctly and put the right number of bytes, 716, because 200, 500, and the 16 in here. But it just didn't cut out the middleman, so I must have forgotten to do that. Coalesce. So what did coalesce actually do? We took middle and bottom, which would have been like this guy and this guy, and it checked if they were adjacent. It wouldn't have been, so it would have skipped it. Then it would have done these two guys, realized that it worked, and it would have said top size, top size of... Okay, I think I see what's happened. Basically, the top's next has to be redirected to point to where the middle's next points. And in a similar sense, if this happens, and I think the middle next needs to point to where the bottom next was pointing. Middle points to where the bottom was pointing. We're skipping over the bottom. Here, top next, if we're coalescing, top next has to point to where next is pointing. Either it's pointing to the bottom next, or it's pointing to bottom, is what that should mean, right? Because top should point to middle, middle should point to bottom originally. And then if we're coalescing, then yeah, I think that's right. So I just forgot to redirect that. Does that look correct? Yeah. 716, 14, 620. If I do this minus this, I should get 0. If I do this minus that, I should get the 48 number. Yeah, 1748. Good. Okay, fantastic. And if I do the last one, I should basically get back the original, what did it originally look like? Compile. Yep. That 16368, which is this minus 16, which is what we wanted, and then this should be the starting address. Yeah, fantastic. Okay, so this test, very small and very plain, worked. Like, it did what I thought, and it seems like the ideas are correct. I could try and look for bugs, but I think the holistic thing is there. I hope that this was clear what happened, but I'm pretty comfortable with how this worked. I'll get rid of this print statement because it's no longer necessary. And yeah, the the actual pointer arithmetic is a bit gross, but I don't know if I can get around it, to be honest. Like, stuff like this is annoying, but I feel like it's sort of necessary. Although, if new header stayed as header T, I would add 1. It's just that because I do that, I add a random number of bytes. I feel like I have to be working in byte star instead of headers. Like, I could do +1. Yeah, I don't think I can. I think it's pretty much as good as it can get. Okay. Cool. I think that made sense. And then basically, you know, the way that you could modify this, or the way you could extend it, is basically I used first fit. You could adjust this to use like the other ones: next fit, worst fit, best fit, like that. They're basically other strategies of deciding which node to use in your free list for an allocation. Next fit is probably the most interesting. Basically, you know, first fit always starts from the start, right? The start of the free list. Next fit keeps track of where your search terminated. Like, you know, you looked for a particular, you know, you were given a particular size that for allocation, you iterated through the free list, you found a place, you keep track of that spot, you keep track of that node, and then in the next allocation, you start searching from that node as opposed to from the start. Start searching from that node, just so that you can kind of keep your scan kind of across the entire list. You're not kind of having bias towards the start of the list. But anyway, this is, you know, it's not a big deal. So you could extend it by doing that, and then you could also, there are also more sophisticated methods of figuring out of doing this free list stuff. Things that are probably a bit more efficient and just use slightly more like reasonable and appropriate data structures to make the actual search and allocation faster. So like using BSTs and stuff. Oh, not BSTs, binary trees. And so there's buddy allocator and segregator list were the examples in the book, but there are others as well. And yeah, it's probably a good read, but for now I'm very happy just to end it there because I think the holistic understanding is there. So yeah. Anyway,